Hello and welcome to Class 3. This is going to be the lecture portion of it. It's going to be pretty short. Maybe I'll do the first example as we're in here. I have a loud talker outside my office. I don't know why people do that. I think they want other people involved in their conversations. Maybe. I don't know. Anyway, here's the bottom line up front. The all-important FBD. And the things that are involved in an FBD is we isolate. We let this thing float up into the air in space. There's the F of free body diagram. And it's the body. In this case, we're starting out with a particle, right? So we have the B of this. And then the diagram, we need certain things in the diagram. For one thing, I want you to declare it's an FBD. Everybody knows it is. And then I want to have a coordinate axis defined, the FBD. Now we place all the forces, and here is the most important thing about the FBD. It's one word. On. We draw all the forces on the body. The forces on the body, right? And some of those forces could be the weight. So that's going to be FC. That's going to be the mass times gravity. I know it's mass, but it's actually weight, right? So you want to multiply the mass times gravity. And that's going to be a force. It's the force the Earth is pulling down on the thing. Gravity's working against me. John Mayer taught me that. And so we want to put all the forces. We also maybe want to include, but lightly drawn, not as important as the forces, but still should be in there, some geometry things that we might want to put on there. And we take a look at all the forces. And quite often what we need to do is actually cut things apart, right? We need to actually cut and see the internal forces. So we're cutting things and we're isolating the body. And then, along with the diagram, we take the sum of the forces in the x direction and the sum of the forces in the y direction. And I've just picked these as examples here. And we always declare what the positive is when we do these. And then we start marching through the thing. And we can see the forces in the x direction. Well, it's going to be negative right here, this FA, right? Because it's going to be the one that's just going to be the opposite. And it's going to be times the sign because it's the opposite of theta A, right? So that's the force in the x direction. And you see the force in the other force in the x direction is going to be from B, FB, and that's going to be positive right there because it's to the right. And FB times the cosine right here because, right, it's going to be onto the adjacent side of that line. And then there's nothing in the C from FC in the x direction. So you can start to see like this relationship. We've developed a relationship between FA and FB right here in this equation. Now, in the y direction, we could see that FA times the cosine of A, because now it's the adjacent one right there. And it's positive because it's up. We see that FB, it's going to be negative because it's going down, and it's the component that's opposite from the angle, so it's the sine of B, theta B. And then we have FC is completely in the negative direction. So, and if we had like two unknowns as part of this, like let's say we didn't know this and we didn't know this. We have two equations and two unknowns. Or maybe we don't know the angles. Maybe one of the angles we don't know. Well, but we do know like one of these forces and we don't know that force. Like this little dude we know how much he's pulling onto the thing and we know what angle that forms. Well, now we can find out what that is and this is because we can like maybe solve. We have two equations and two unknowns. This is the big idea. This is the bottom line up front, right? What you need to know is you need to draw a free body diagram and have all these parts to it and set it up. Now, most everything else I've just said, but I want to walk through the book because we want to use the book as a tool, right? And so here's the big operative phrase in here. When the resultant of all the forces acting on a particle is zero, the particle is in equilibrium, right? So that's what we're looking for, equilibrium. What we will find, what's going to be different than what we had before is we were looking for a resultant, which was essentially an equivalent force to replace the forces that we were looking at. Now that resultant is going to be 0. So what we're going to do is we're going to find that something is happening. And quite often what we're going to find, we're going to introduce the idea of the reaction force, the reaction. And that's going to mean equal and opposite, right? And we want to make sure that we recall, right, as we're going through here, that the sum of the force is equal to 0 here, that this is a vector, right? And that resultant is equal to 0. And because it's a vector, we could break it up into x and y components, or into z components too, x, y, and z. But the sum of the force is equal to 0 in the x direction, sum of the forces in the y equal. Now, the book does go through a bunch of triangles and that kind of thing method, and I'm going to not bother with that. Because I think that it kind of distracts. It's just an extra way to solve the thing. And I think the free body diagram is so important. We're going to go to it and we're going to stick with it. These other ideas, they're nice. So they use this like force triangle thing. I'm not going to go do that. I'm asking you not to look at the thing. It makes a lot more, I mean, it is really what we've done previously with the resultant, but the most important thing for us is the free body diagram. So we start off with what they call a space diagram, and we cut the chords onto the thing, and we show just the particle, and we put all the forces on there. I'll also mention that I am going to not use capital T with subscripts. I'm almost always going to make a force an F, and I might make a reaction an R. It's a force of habit. But this is Newton's first law. Something that we want to also introduce is the idea of Newton's third law, right? So sometimes I will refer to this as N1L is Newton's first law. Newton's second law, remember, that's the equal and opposite reaction force, right? So if something is attached to some point and we want to know some forces on it, we need to remove it from where it's attached, and we're going to end up finding reaction forces soon. I don't think that really happens in this particular lesson. So let me take a look quickly. I will discard this stuff here, but let me discard that and see how long. It's only a 7-minute video. I think I'm going to call it. Let's call it. We're done.